Okay, alright. Hello everyone and welcome to another episode of Power Logic. So today we're gonna be going on to number 24. The figure below depicts a regular 7-gon inscribed in a unit circle. What is the sum of the fourth powers of length of all 21 of its edges and diagonals? By the way, you might ask, why is it 21? Because we have 7 points, and any 2 points within the 7-gon is gonna, within the heptagon, is gonna create an edge or a diagonal. So they're just simply gonna be 7 choose 2, which is 21, which corresponds to the number given. So it's not just a random number. And now how are we gonna start with this? Because 7 is actually a number that's not really fun to deal with when doing angle problem, since 7 is not even a divisor of 360, so essentially it's kind of tricky. And by the way, the answer just seems to be really nice, and they ironically, or like just surprisingly, they're actually all divisible by 7. This just seems to be a funny fun fact. So I'm gonna present 2 solutions. Now let's just go on to solution number 1, which I want to just add a quote to there because that's not really a rigorous solution. So for solution 1, we're gonna think about general case and find patterns. So essentially, let's say if I have a unit circle, and what if it's not a heptagon but actually a triangle? And we just do another case. What if now we have a square and the motivation of this just comes that all of the answer choices are divisible by 7, so they're probably just gonna be a pattern. So let's just start with the case of the triangle. Now since it's in a unit circle, then these are simply just all 1, and because this is actually 120 degrees, so we know that this one is actually square root of 3, and square root of 3 for all of 3. So now, because in triangle there's actually no diagonal, so therefore the answer will just be root 3 to the 4th times 3, which is equal to simply 3 times 3 squared, which is equal to 27. Now let's go on to a square. So square, we're gonna draw a connection. And notice that these 4 are radius 1, 1, 1, 1. And because of symmetry, we know that these 4 are actually all right angles. So this is gonna be root 2, root 2, root 2, and the square root of 2. So now because the diagonal in this case is actually going to be the entire diagonal, so essentially the diagonal would actually have a length of 2. So therefore the answer to here is going to be 4 times root 2 square root of 2 to the 4th power, since we actually have 4 lengths of square root of 2, which are the edges. Then we add 2 times 2 to the 4th, because we have 2 diagonals and each diagonal has a length of 2, and we're raising everything to the 4th power. So this one is just 4 times 2 squared plus 2 times 2 to the 4th equal to 32 plus 16 equal to 48. Alright, now 5-gon just does not seem too easy to deal with, So let's actually do one with a hexagon. So in a hexagon, we know that all of these are actually 120 degrees. So these are actually composed of 6 equilateral triangle. Okay, so this means that all of these are 1, and simply these are just also all 1s. Now we don't want to skip some of the cases because theoretically there are 6 choose 2 equals to 15 different diagonals and edges, so therefore we have to account for the others. We're gonna have one in this shape, one in this shape. So now we actually have 6 edges. And let's look at these longer diagonals. How many of these are there? Because keep in mind we actually have to add up to 15. So now we're gonna know that whether we overcounted or undercounted. So these are gonna have 1, 2, and 3 of them. These. So they're gonna be 3 such long diagonals, and we're also gonna have 1, 2, 3, 4, 5, 6. So essentially the answer is going to be equal to 6 times 1 to the 4th plus 3 times the length of the longer diagonal, but longer diagonal, you can see that this length is root 3 and this length is going to be 2. So plus 3 times 2 square, and then plus, well, what is the length of the shorter diagonal? Well, the length is just going to be this. And we just simply do law of cosines on this triangle. We're going to get that this is actually square root of 3. So plus 6 times square root of 3 to the 4th. Actually, excuse me, this one should be a 4. Now that's just some simple computation that we have to do. 6 times 1 plus, well, square root of 3 to the 4th is 3 squared. And then plus 3 times 16, and that is going to be equal to 60 plus 48, which is 108. Okay, now let's look at these numbers. 27, 48, and 108. Are there any commonalities between these numbers? Oh yes, this one is 3 times 3 square, and 48 is equal to 3 times 4 square. And clearly 108 is equal to 3 times 6 square. Okay, it seems like that there's a pattern, or yeah, there's a pattern that the quantity that the question asks for any n-gon is gonna be 3 n square. Now, if it's unrigorous by the principle of engineering induction, we call this to be engineering because we don't really have a rigorous proof on why this is true. By the principle of engineering induction, then the answer is just 3 times 7 squared, which is equal to 147. But you know, that is just not how we're gonna solve this problem because it's just too based on assumptions. So we're gonna actually solve this rigorously. So now, we notice that there's actually 3 types of lengths. There's one in this, and another one that looks like this, and another that looks like this. And we actually have 7 lengths, 7 segments for each of these categories. And we're gonna draw radius. So now we're only gonna look at this triangle, this isosceles triangle. And both of these are 1. So now, because we know that the sum of the interior angles is going to be equal to, or the sum of the angles from the middle is going to be equal to 2 pi, since we're actually dealing in radians. So this angle is going to be 2 pi over 7. So now what is going to be this angle? Because it's isosceles, then these 2 angles are actually congruent. And their measure is not that hard to calculate. It's just going to be pi minus 2 pi over 7, and I think divided by 2, which is 5 pi over 14. Okay, so now we have the angle over here. We have the angle over here, and we have the side lengths. Now is a good time to solve by using the law of sines. We're gonna say that this one is gonna be equal to d. Then from law of sines, we're gonna get d over sine of 2 pi over 7 is actually equal to 1 over sine of 5 pi over 14. Okay, so now we're just gonna isolate d is equal to sine pi over 14. Oh wait, d is actually equal to, d is equal to sine of 2 pi over 7 over sine of 5 pi over 14. And is there a way to simplify this? Well, yeah, because 5 pi 14 is actually equal to pi over 2 minus 2 pi, actually minus pi over 7. So, now because we know that sine of theta is equal to cosine pi over 2 minus theta, and that is actually an important trig identity that is derived from angle addition, angle subtraction formula, then this one can actually be further simplified into sine of 2 pi over 7, or divide. We're gonna divide by actually cosine of pi over 7. Now this looks much nicer, and in fact this one is actually equal to 2 times sine of pi over 7 cosine of pi over 7, since this actually comes from double angle identity. So therefore this d simply just becomes 2 sine of pi over 7. Alright, so we actually finally got that this is equal to 2 sine of pi over 7. Now, how are we going to find the green or the red line segment? Now, if we want to find the length of the green segment, then we can simply just look at this triangle over here. Now, this triangle, since we know that it's a regular hexagon, so therefore all of these sides are going to be 2 sine of pi over 7 and 2 sine of pi over 7. Now we know that, well, because the sum of the interior angles is going to be 180 times n minus 2, and there are 7 angles that are congruent, so we're going to divide by n. That is just equal to 900 over 7, which converted to radius is going to be 5 over 7 pi. So this angle is actually 5 pi over 7, and these two angles simply are just pi over 7 and pi over 7. Well, these just comes from pi minus 5 pi over 7, and since these two are equal, divide by 2 gives us pi over 7. So now we're just gonna do another law of sines. Just call this to be d2, I don't know, d2 over sine of 5 pi over 7 is equal to 2 sine of pi over 7 and divide by sine of pi over 7. These two cancels out, so we're only left with 2. Then you multiply to the other side, we're gonna get that d2 to sine of 5 pi over 7 times 2, which actually we can just convert it to be 2 sine of 2 pi over 7, because we know that sine of pi minus theta is equal to sine of theta. And that is actually another identity that is important and is proved by angle additional formula. Okay, so we got another length, and the green length, sine of 2 pi over 7 times 2. Okay, finally, the red length. Well, how are we gonna solve that, since it seems like we cannot have anything good with these? Now we're gonna look at this triangle. Let's just draw another one outside this triangle. In this triangle, we know that this angle is 5 pi over 7. What about this angle? Well, now remember that this triangle is actually one part of this entire trapezoid. So therefore, we can in fact complete this trapezoid. And because it's a trapezoid, forgot how to erase, but because it's a trapezoid, then this angle is 5 pi over 7, corresponding to one of the interior angles, and because it's trapezoid, then this angle is also 5 pi over 7. And since it's isosceles trapezoid, then this angle is going to be the supplementary angle of 5 pi over 7, which is just 2 pi over 7. And so does this angle, 2 pi over 7. Now let's just look at this triangle again. This triangle again. Then these lengths are the same. So therefore, this tiny angle right over here is going to be pi minus 5 over 7 pi divided by 2, which is pi over 7. And that is actually the same with this angle, pi over 7. So we now know that this angle is actually 4 pi over 7. This angle is pi over 7, while the angle over here is just 2 pi over 7. So we're just gonna ignore this part, and we're just gonna look at the bottom, the bottom part of the triangle, the bottom part of the trapezoid. So from what we have discovered, then this length is actually 2 sine of 2 pi over 7, and this length is 2 sine of pi over 7. Okay, so now this length, I just call it to be x. Then we can just do a law of sines, but just use any of these two lengths. I mean, that doesn't really matter. So we're just gonna use the one with 2 pi over 7. 2 sine of 2 pi over 7 over 7. That's actually equal to x over sine of 4 pi over 7. Now these two cancels out, which is similar to the previous one, and we're just gonna get x is equal to 2 sine of 4 pi 7, which is just equal to 2 sine of 3 pi over 7. Okay, we actually got all the lengths, even though the length just is not in our favor. 2 sine of 3 pi over 7. So now the question just remains that what is the value of 2 sine of pi over 7 cube, no, fourth, plus 2 sine of 2 plus 2 sine of 2 pi over 7 to the fourth. Oopsies. Plus 2 sine of 3 pi over 7 to the fourth. What is even this value? We know that. And the part hard is that we don't know any of these values. So how are we gonna know the answer when they're raised to the fourth power? And you might ask, well, there's 7 of them. Well, we just multiply this by 7 simply. And in fact, we can also take one part out, 7 times 2 to the fourth, and then times sine 4 sine to the fourth of pi over 7 plus sine to the fourth of 2 pi over 7 plus sine to the fourth of 3 pi over 7. What is even this value? Okay, so now we're going to explore into some properties of a unit circle. So we have a unit circle right over here. So in high school math, you guys might have learned that if we have if we just draw a right triangle here, now because this one is actually 1, then we have a theta over here. Just gonna call it phi, then this part is simply cosine of phi, and this altitude is gonna be sine of phi. Now, what if I reflect this downward? Then, well, let me just use a different color for the sake of clarity. So I'm gonna make a reflection downward. So this angle is actually still phi, but we're gonna write this as negative phi because it's actually angle but below the x-axis. So now, the magnitude of this is still sine of phi, but this point is just gonna be cosine of phi, but negative sine phi. But the point at the top is actually cosine of phi and sine of phi. Alright. So now what if we just express this in a convex plane? Then, well, this one is actually going to be expressed as cosine of phi plus I times sine of phi. And the bottom is going to be equal to cosine of phi minus I sine of phi. Well, why are we going to express as this? Because you know that when you have like a convex plane that represents a plus bi, then the endpoint is going to be a comma b. So that is why this is true. So now, how are we going to find the sine value of phi? Now you can see that if I let this, or if I let this complex number be equal to z1, and let this part be z2, then we can just isolate these. So we're gonna get that z1 minus d2. Since if we do z1 minus d2, then cosine phi is gonna cancel out. z1 minus d2 is equal to 2i sine phi. So z1 minus d2 over 2i be equal to sine of phi. Now, for the sake of time, we're just gonna cite the theorem that e to the I theta is equal to cosine of theta plus I times sine of theta. And that is in fact the famous Euler's identity, and if you are curious about the proof of this, just go and check my video in the back about Taylor series and the proof of this. So essentially, from here we're just gonna see that sine of theta is gonna be equal to e to the I theta minus e to the negative I theta over 2i. And essentially for this one, we are just literally using this thing that we came up with. So okay, so how is this gonna help us? Well, now we're gonna use a little bit of roots of unity. So we're gonna let z be the 7th roots of unity. By roots of unity is basically the solution to It's basically the solutions to the equation z to the 7 minus 1 is equal to 0. There are actually 7 roots because of the fundamental theorem of algebra, but we can only see one, which is z equal to 1, and the other 6 are in fact on the complex plane. So essentially these are all the roots, and you can see that these 7 roots actually forms a circle, which is actually the unit heptagon. Okay, so well, e to the I theta, so we can just use this to rewrite this thing. So what do we want to find the value of sine of pi over 7? Sine of pi over 7 is equal to e to the pi over 7i minus e to the negative pi over 7i. The entire thing divided by 2i. Okay, so this one is actually expressed as z minus z to the negative 1 over 2i. Well, you might be a little bit confused about this, but you can just go back to what's happening right here and here to see that, to gain some kind of intuition. Now, sine of 2 pi over 7, that is equal to e to the 2 pi I over 7 minus e to the negative 2 pi I over 7 over 2i. Which simply just give us z squared minus z to the negative 2 over 2i. So sine of 3 pi over 7, that is equal to e to the 3 pi I over 7 minus e to the negative 3 pi I over 7 divided by 2i, which is simply just equal to z cubed minus z to the negative 3's power over 2i. So now we can just add the sum force power up. That is simply z minus z to the negative 1 to the fourth plus z squared minus z to the negative 2 all the way to the fourth power, and then plus z cubed minus z to the negative 3 to the fourth power. The entire thing we're gonna divide by 2i to the fourth power, because we can see that each of these there's a coefficient of 2i on the denominator, so we're just gonna pull all of these out. Now don't forget that since we have 7 and we also have a 2 in front of all the sign values, multiplied by 2 to the fourth. Now, in fact, funny fact, these two actually cancels out since I to the fourth is actually equal to 1. So we actually have this expression. Now how are we gonna evaluate this? Now we just expand. So z minus 1 over z to the fourth, that is equal to z to the fourth minus, we're just gonna expand using binomial theorem. 4 choose 1 times z cubed times 1 over z plus 6 plus 4 choose 2 z squared times 1 over z squared. Now minus 4 choose 3 times z times 1 over z cubed, and then minus 4 choose 4 times plus 4 choose 4 times 1 over z to the 4th power. Okay, now after all of these, we can just combine to be z to the 4th minus 4z squared, then minus, and then plus 6 minus 4z to the negative 2, then plus z to the negative 4. That's a lot of work, but we still have to do it. Now, you might realize that about the coefficient. Not the coefficient, but all of these powers. 4, 2, 0, negative 2, 4. So because we see that every time we're gonna, like, if we add an n to here, then every time we're gonna subtract off by 2n. So essentially, the next series of terms are gonna be 8, 4, 0, negative 4, 8. This is since, well, if we have zn minus 1 over zn to the 4th, then the maximum is gonna be 4n. But then we're gonna keep on subtracting 2n from it. So therefore, we know that the next series of terms are going to be 12, 6, 0, negative 6, and negative 12. These are just the series of the exponents right over here. So now, because we know that 7th roots of unity always comes in integers less than 7, so therefore, we're just going to take mod 7. Well, this one's actually 1 mod 7, and negative 4 mod 7 is simply just 3 mod 7. And 8 is just 1 mod 7, 12, 5 mod 7, 6 is just 6, 0 is just 0, negative 6 is 1 mod 7, and negative 12 is going to be negative 5 mod 7, which is 2 mod 7. So ignore all the zeros, because zeros is simply just, there's no coefficients, there's no exponents, so it's just going to be 1. So essentially, these actually sums up to 18. And now you can see that for these coefficients, well, actually I have to convert this one, negative 2 mod 7 is just 5. Now the thing that we subtract are 2, 5, 4, 3, 6, 1, and the thing that we add are, wait, this is actually negative 4, so essentially this is going to be 3. So the thing we subtract are 2, 5, 4, 3, 6, 1, and the thing we add are 4, 3, well actually this is still negative 1, this is negative 8, so this is going to be 6. Sorry for this mistake. But now you can see that the thing we're adding are 4, 3, 1, 6, 5, 2, and the thing we're subtracting are 2, 5, 4, 3, 6, 1. So these are actually the same value, but we subtract 4 times, but we add 1 time. So we're going to subtract this set. So essentially the thing that's inside is going to be 18 minus 3 times z plus z squared plus z cubed plus z fourths plus z fifths plus z sixths. And that we just multiply this by 7. So because z is actually a solution to z to the 7 minus 1 is equal to 0. By Vieta's, we know that the sum of solutions are going to be equal to 0. But notice that the sum is actually going to be 1z, z squared, z cubed, z7. So we actually subtract 1 from the sum, we're going to get that this sum is actually in fact equal to negative 1. So essentially, this is going to be 7 times 21, which is 147. And that actually gives us answer choice C, and we are finally done. Thank you for watching, hope you enjoyed, and I'll see you in the final video of the 2022 AMC 12B solutions. Stay tuned.